Hey guys, welcome to day 10. We're going to be continuing on with our discussion of imaginary numbers in this particular lesson. In the last lesson, we learned what an imaginary number was, and we also learned how to do some operations with those imaginary numbers. So, like, how do we square them? How do we multiply them? How do we raise them to certain powers and things like that? And what we're going to see today is where these complex numbers or these imaginary numbers pop up in algebra. And so that way we know that when we run into them, we know how to deal with them. Okay, so let's take a look at this first problem. So this is a pretty typical problem. We've seen this many times before where they give us a quadratic and they ask us to find the roots. Okay, so roots are the same thing as x-intercepts and the same thing as zeros. So zeros, roots, x-intercepts, typically all the same thing. It's just how you write the answer at the end, that determines the difference between a root and an x-intercept. So what we've done before for a problem like this is we have tried to factor. Okay, so I'm going to attempt to factor this thing, and let's see what happens when I do. So I draw my box, and I insert the first and the last term into that first diagonal. So the x squared goes up here, the 5 goes here, and I'm going to draw my diamond. And remember, I multiply that first diagonal to get the top, so we've got 5x squared. The middle term goes in the bottom of the diamond, so we've got negative 4x. And then we try to find two numbers that multiply to give us a 5, but add to give us a negative 4. Okay, so there's really only one way to multiply to 5, and that's with a 5 and a 1. Okay, so I can make this 5x and 1x. Now, if I leave it just like this and I do 5 times 1, I get the 5, but 5 plus 1 gives me a 6, not a negative 4. So my other option might be to make these negative, right? If I made them both negative, well, negative 5 times negative 1 gives me the positive 5. But again, when I add these together, I don't get negative 4, I get negative 6. So then the other option would be to make one positive, one negative, right? So if I do that, let's say I make this one be positive, well, negative 5 times positive 1 is a negative 5, but I needed a positive 5. All right, so what we're seeing here is that this one is not factorable. There's not going to be any combination of two numbers that's going to work here. So this one's not factorable. All right. So we have to use an alternative method to try and find the roots. And this is where the quadratic formula comes in handy because not every quadratic is factorable, but the quadratic formula will work on every single quadratic. All right, so let's see what happens here. So remember, quadratic formula, we need to know what a, b, and c are. So in this one, a is going to be 1 since there's no number in front of the x. B is going to be negative 4, and c is going to be 5. Okay, and I'm going to plug that into my quadratic formula. So we've got negative 4 plus or minus the square roots. And this will be negative 4 squared, right? B squared minus 4ac. Right, so 4 times 1 times 5. Go, and then I'm going to divide all of this by 2 times a. So 2 times 1 is just 2. All right, and then I go through and I like to simplify step by step. So I see a pair of negatives there, so that'll just become a positive 4, plus or minus, and then I start working inside of the square root. This is going to become a positive 16. All right, don't forget about the parentheses when you put that in the calculator. And this will be minus, and then 4 times 1 times 5 is 20. So I have 16 minus 20, and then this will all be over 2. And then I just keep working. So I can do 16 minus 20 inside of the square root. So I've got 4 plus or minus the square root of negative 4 over 2. All right, and this is where we start to see the problem. We've ran into quadratic formulas where this has happened before, where we end up taking the square root of a negative number, and we've always told you when this happens, you get to say no real answers. And now that we know about complex numbers, we really know what this is now. Okay, so we can't say that there's no answers to this. We can say there's no real solutions, but there are some complex solutions for the roots of this thing. Okay, so we know from the previous notes that that square root of negative 4 is simply 2i. So I can say 4 plus or minus 2i all over 2. Okay, so we don't have to stop here anymore now that we know about the complex numbers. We can keep going by simplifying this into its complex form. All right. And then we can simplify it a little bit more with the fractions. So since the 2 in the bottom here goes into the 4 and the 2, we can reduce both of those. And what we're going to get is 2 plus 2i and 2 minus, not 2i, 2 plus 1i. So this will be 2 plus 1i, and this will be 2 minus 1i. And these are our roots. These are the complex roots. Okay? So they're not real number roots, they are complex number roots, and every quadratic will have roots, whether they are complex or whether or not they are regular numbers like we've dealt with before. So these are the roots for this quadratic. Okay, and you'll notice that I kind of left this. We can't do 2 plus 1i. One has an I and one doesn't, so we can't combine those and say 3i. So don't try and do that. Just keep them separate, and you'll notice down here that any number in this form is called a complex number, even though it has a real part. Like this 2 is a regular number, that's okay. All right, so you might see numbers that kind of look like that. So some examples of this a plus bi format is just like what you saw in this problem here. So 2 plus I is an example of a complex number because the 2 is what we call the real part and the I is the complex part. So that's the a and the bi part, okay? We've also seen complex numbers where, for instance, we've just had 3i just by itself. All that means is that there was a 0 there for the real part. Okay, so the a part would be a 0 in this case. So 0 plus 3i is its complex form. All right, another one that I want to show you, because we'll run into this when we do more complex problems, is something like this where we have 3 plus 5i, 3 plus 5i over 2. Okay, so it's kind of like a big fraction. We'll run into this because we'll be using quadratic formula quite a bit. And when you run into a complex number that's like this, it is okay to just leave it just like this. You don't have to simplify this anymore. And the reason being is because when we look at the fraction, 3 is not divisible by 2 and neither is the 5. So this one does not reduce. Okay, so this one doesn't reduce. And you can just leave your complex number like this. Versus something like this, where if I had 4 plus 8i over 2, this one does reduce because the 2 goes into the 4 as well as the 8. So this one would reduce to 2 plus 4i. Okay, so this one does reduce, whereas this one doesn't. All right, so this is 4 examples of complex numbers and the different forms that we'll run into when we do these problems. Okay. So one more thing that I want to show you today, I want to show you this from a graphical perspective. We've also found roots just by looking at the graph because we can look at the x-intercepts of the parabola to find the roots. We've seen that in previous lessons. So this quadratic, x plus 3 squared minus 4, is graphed right here, and we can see the x-intercepts located at -5, 0, and -1, 0, which means the roots are -5 and -1. So it's a quadratic, it has 2 roots, and these are the 2 roots. We can see those on the graph, okay? So then let's take a look at this quadratic in part B. This is x plus 3 squared. We notice that this factor has a power of 2, so this is going to create what's called a double root. And from the previous lessons, we know that when we have a double root, we're going to see the function bounce off of that x-intercept. So if we track this parabola down to its x-intercept, we see it hits -3 and then bounces right back up. That's because it's a double root. So this has a root of -3, but it still has 2 roots because that -3 has what we call a multiplicity of 2. So the -3 happens twice. It's the same number twice. All right. So now we go to this one, part C. We got x plus 3 squared plus 4. And when I look at the graph, this is a parabola that's been shifted left 3 and up 4 based on this graphing form that we see here. And it opens upwards. So this is never going to hit the x-axis. So this one doesn't have any real roots. Okay, so we can say no real roots. And this is kind of like the one that we did algebraically in the last example. It has no real roots, but it does have two complex roots. We will not be able to see complex roots on the graph. Okay, so make sure you make a mental note. If you have a parabola that's like this, it doesn't have any x-intercepts, that means it has two complex roots. Okay, no real roots, but it has two complex roots. All right, and that's what those are the three different situations that you can see graphically when we're talking about the roots. You can have something with two roots, one root, or no real roots, and those two roots are going to end up being complex. All right, so that's enough for today for day 9. It's about 10 minutes of stuff there to talk about. We'll come back tomorrow and we'll look at some of these practice problems together just to kind of work through some of the different scenarios that we'll see, and we'll use this stuff that we just talked about. All right. Okay, guys. Have a great day.